I'm glad you could join us today for another learning session online. Today is an HSW opportunity for you. You'll get one health, safety, and welfare credit for attending today's session. You'll need to have RSVP'd online by the calendar event for today's session, which is how most of you got here. In case you're joining us outside of that, we do have that link in the chat function on your Zoom platform. So use that RSVP link to make sure that your name is credited for today. And then of course, we want you to stick around through the whole presentation to ensure you get that hour credit for the learning that you'll receive. Also, there's a Q&A function. So if you have questions that come up as you hear the content, we encourage you to put those questions into the Q&A chat function. It is different and distinct from the chat, however, so you'll see that alongside the chat next to the share screen function on the bottom of your Zoom platform bar. Today we've got a very interesting and somewhat technical conversation today with some of the best in the business on this topic. The topic is bridging and thermal continuity of the building skin, balancing thermal separation with structural support. Our presenter today is Will Babbington. Will is an AIA member, a PE, and also lead AP Building Design and Construction certified. He's a facade design director and a principal at Studio NYL. He's both an architect and engineer who has designed and realized award-winning structural and skin projects that merge high performance, high design, and constructability. Will's the current national chair for the Building Enclosure Council and representative for AIA National on the ASHRAE 90.1 envelope subcommittee. He's also an ASTM Committee E06 on performance of buildings and is a developer and trainer for ASTM's and NIB's new Building Enclosure Commissioning Certificate Program, known as BECX. But without further ado, and with many thanks to Will for joining us and sharing his expertise today, I'll turn it over to Will and take it away.
All right, thanks, Mike. I appreciate the kind intro there, and thanks everyone for taking the time to join me and take a listen to what we have to say here, especially after a hopefully what was good holiday weekend, and hopefully this will ease you back into everything nicely and smoothly. As you can see, the title here is a little bit different. I continuously tweak it a little bit just to try to get something a little bit more clever, but the content's more or less the same. And here we're calling separating the inseparable, balancing a thermal separation with structural continuity. But just to give you a little bit of background, I'm the facade design director and principal at Studio NYL on the skins group side. Architect and engineer, as Mike was saying, Building Enclosure Council's national chair, as well as past chair for the local chapter. And also, you know, quite a few other things in my quote-unquote spare time, but one that's particularly pertinent to what we're going to be discussing today is ASHRAE 90.1 envelope subcommittee. AIA National's one of two representatives on the subcommittee, and the reason why that's pertinent is because there's some provisions that we're marching towards that will deal with thermal bridging. So just a little background, Studio NYL. NY is New York, L is London for Chris O'Hara from New York and Julian Lynham from London, founding principals, if you're not familiar with us. We're out of Boulder, but have some satellite offices, a sub office here in Denver, but satellite offices in Minneapolis and Boston. Primarily a structural firm, that's our roots. But through some specializations in glass engineering, we evolved a skins group. And differentiating ourselves not only by offering full technical services, but also specializing in the marriage of high performance and high design, highly collaborative, not just there to find that solution, but to help explore the question. And also looking at starting at those first level principles, breaking things down for a holistic solution, which you'll see a lot of in these examples that we'll have today. Even though it looks like a very complicated facade system, which it is often, very, very simple in the roots in order to get it realized both new construction as well as existing construction, marriage of the two. Also, a little bit local here. Here's one on the boards up in Boulder. One we've completed here downtown Denver, all different project types, scales, Rams Charger Stadium in LA, and all the way down to those smaller, more modest designs here with Pyatt Studio out of Boulder. So there's our spiel, basically who we are, what we do. And now we'll get into the heart of the presentation since we've got quite a bit to cover. And I understand questions are going to be accrued, and Mike's going to start divvying them up to me at the end. So I'm looking forward to those, but we'll dive right in. So starting really basic here, obviously with anybody who's done any wall design, built any walls, know that there are a vast number of variables in facade design, and many of these variables are interrelated, dependent, and perhaps none are more contradictory as structural and thermal. Taking a step back, looking back in the day when walls began with just that one layer where structure was also your moisture, your thermal, and your, to a certain extent, air barrier, if you will, a simple separator, really more of a filter stacking dirt, rocks, and wood. And then over time, we started to care more about that occupant comfort, started figuring out ways how to keep that heat that was generated within, or coolness that was generated by that shielding of the interior envelope, and started caring about thermal performance. So obviously the stud cavity insulation wall was good back then, and belongs back then, because we've learned that by seeing the writing on the wall, so to speak, the image to the left obviously showing some wall ghosting, and outside images that you could see in the winter where you see the roofs with their frost ghosting. And then if you have access to the internet or even thermographic camera yourself, you can see that thermal shine, is what we like to call it, come through wherever we have those thermal bridges in the walls. Getting to the nitty-gritty, the codified definition of what a thermal bridge is, basically where you have a higher thermal conductivity versus your surrounding conductances in that wall assembly. So taking that into account, standards and codes then started to realize, well, we've got a problem with that. So let's place exterior insulation. And that worked well. It also worked well with these rain screen assemblies, which add to a little bit of the durability and redundancy in wall systems from a standpoint of moisture and air. However, we realized that, you know, it's not just the primary, secondary structure, it's that tertiary structure, if you will. We've got to connect that cladding back to the secondary or primary structure. So we started giving that continuous insulation a little bit more of a definition. And ASHRAE's pretty specific on what they called continuous insulation. Basically, nothing allowed through that exterior layer of that continuous insulation except for fasteners and service openings. But that was disregarded to a large extent for a number of reasons. So we also realized that, you know, we have other areas other than just the cladding connections, especially at those floor and balcony slabs, parapets, which is basically that floor to wall intersection that you see on the left there, except with a radiator fin tube shooting out of the top. And then all the way to your glazing transitions between opaque and fenestration. Moreover, we're trying to pay attention to the fact that the thermal bridging isn't just an issue in terms of energy expenditure, but when you factor in the condensation related damages potential based on sensitivities to moisture for your interior finishes. Not only that, but the health and safety of your occupants with that nice black mold there at the base, as well as to the simple comfort of your occupants. It's got a wide-reaching effect on multiple facets. Moreover, when we start looking at high-performance buildings with any of these aspects, NREL and another, quite a few other entities have realized that the envelope is really where we should be placing all of our primary focus on the first method to creating these low-energy buildings. They're saying that, quote, low-energy architecture is not effective if mechanical systems have to solve the problems that result from envelope design. And so that percentage better was not producing consistent results, and there was a lot of opportunity for gaining that was a diminishing returns. And so there's a push for modeling that better reflects the reality. And out of that spun a ASHRAE research project report conducted by Morrison Hershfield, where they got this super high-end thermal modeling program based in the aerospace and automotive industries, which took into account 3D effects and had validated results, which looked at many wall conditions as well as wall floor intersections and whatnot, basically taking to heart and exacting our motto really that we carry at Studio NYL, like if you can't measure it, you can't manage it. So we're trying to link that to the whole building energy models and seeing what kind of buildings will benefit the most from these different effects and accounting for them, which have a wide variety of variables in and of themselves. This had morphed into a usable document, more in its purest form really with British Columbian Hydro, which is Canada's version, I guess, up in British Columbia, almost like an Excel and energy consortium where they're trying to account for these thermal bridges since they've got some real skin in the game in terms of the energy usage. This is really taking into account doing comprehensive transmittance calculations or using direct values from basically the basis of that previous research project. Now, in the U.S., not to be outdone, to make use of the money that they spend on their own research project, ASHRAE is taking steps into accounting for thermal bridging. It's a more prescriptive approach than BC Hydro's, but also takes into account, market transformation being incremental towards improving the whole building energy performance, takes into account constructability, economics, and also trying to make it accessible to code officials. So it's not quite as full bore as a BC Hydro, but it does cover quite a few options. So you can see on the screen, the key points are, really looking at those wall floor roof intersections, including parapets, point penetrations, as well as the opaque fenestration transitions. It also deals with clear fields, like wall cladding attachments, within the prescriptive values, which are embedded in there, but we'll get into that a little bit more. But pretty much it's going to be applicable if you're in any mixed or heating climate zones. So if you're in 4 through 8 there, this is going to be important for you. It's going to be very pertinent. There are additional documentation requirements, which it's important to know. Your drawing should have insulation type and rated R values listed very clearly, dorm fenestration schedule, performance values, and also have an additional plan calling out space conditioning and daylit areas so that the code official can connect the dots really between the design. It's going to cover quite a few, again, in a prescriptive manner, guidelines for opaque to vertical fenestration, basically the alignment of insulation between your center glass and your exterior insulation line, or require you to have what we call a diving board, or some people call a window buck, which we'll show in some later details, which needs to be made out of wood, an inch and a half thick, or some other material with a R value of 3 at the very least. It also talks about exterior cladding support systems based on materials, steel, having a maximum cross-sectional area of 1.5 square inches, which is based off a 3/4 or 3/8 inch diameter fastener poking through there, or you get a little bit more area if you use stainless steel due to the lower conductivity, and goes on and on. Mass walls, it has quite a few additional provisions, which I won't get into too much here, not only because this is a draft, but also because mass walls aren't such a static performance. They've, in terms of them being a thermal creature in and of themselves, they're a little bit more dynamic in terms of the thermal lag that we're often after when we deal with mass walls. So, and the thought is that we'll have several diagrams giving some guidelines on some assemblies, but we can't cover them all, but it gets to the gist of, you can see with the parapets, wrapping insulation around, making it continuous from the roof as it falls over the wall, and those roof wall intersections, and where it can't, where you have interior insulation, you're going to have a little bit of an overlap to deal with the bridging at those joints. So really getting to basics, we're calling out, you've heard me mention clear field thermal bridging. These are bridges that occur at a fairly frequent spacing where it makes it more or less continuous, but a bunch of points or a bunch of lines, and these are like your steel studs and joists, your subgirts for rain screen systems, the masonry units, webs and ties, and the fasteners that we talked about. Kind of concentrating those, that clear field bridge. If you look at a linear, is the next type. So for your example, shown on the screen here, your balcony or canopy penetrations through a wall. Also looking at those parapet conditions. And again, they're carrying that psi factor. If you're not up to date on your Greek in that bottom right, that's what that's what we're calling there. So that's applied for kind of an energy factor for these linear bridging elements. And again, this is a very, very significant one, accounting for up to 70% of the total opaque wall's heat flow. So one that the code is definitely trying to hone in on. And then looking at using your chi factor really to account for your point bridges, your beams penetrating through a wall to pick up canopies, a column penetrating through a roof or floor, are other examples of these. And then when you go ahead and take your final model for your whole building analysis and give that to your energy modeler, this is the equation that you're using. You're basically accounting for your clear field bridging to the left, adding that with your total lengths accounted for with those psi factors, and then going with the chi factors and the number of your point bridges, dividing by the total area. So area weighted-ish, and also don't start freaking out here. I'm not going to make you break out the calculator, but it's going to be important also just to take maybe another step back and take a little thermal review here, if you will. So when you're looking back at your thermodynamics course, or maybe your environmental control systems course load, we're looking at 3 modes of heat transfer: radiation, convection, and conduction. Here exemplified with your IGU. The one that we're going to be focusing on with thermal bridging is that conduction, the physical contact between different materials from the exterior to the interior. But in order to ignore other modes of heat transfer, especially in the opaque, obviously we can get rid of the radiation for the most part, but especially with the convection, we need to make sure that prerequisite to all of this, our detailing and whatnot, when we're out in the field, we need to make sure that there aren't any gaps in the insulation. Otherwise, you get what they call wind washing, and we kind of have a short circuit, and all bets are off, really, in terms of the assumptions. In terms of our structural review, basically looking at 3 different loading types: axial, which consists of tension and compression, shear, and bending. Of course, with axial compression especially, short columns behave a little bit different than your long, slender columns because of that lateral torsional buckling, where we can get some kick out. And then also with your shear, where you're tearing apart, it's a little bit easier to deal with also in your thermal bridging connections, which we'll see here a little bit later. And then bending, which is the most difficult to deal with, and also the least efficient way of load transfer, and is of course the combination of compression and tension. So now we can start getting into a little bit more the materials. I mean, obviously we've been talking about conductivities and thermal conductance, and as you can see, these are some of our projects. We, like lots of other architects and engineers, we love our materials at Studio NYL. Materials good for thermal components and structural components, and so it would make sense just to go ahead and select those materials which can do a little bit of both and have that overlap, and call it a day and just start detailing like we have in the past. However, it's unfortunately not that easy, though. It tends to be that the materials that are great at structural load transfer are very poor at thermal performance, and conversely, the thermal insulation materials tend to be not so hot at carrying a load. Even when we start to break into NASA's thermal material candy store and apply that to the building industry, with the silicone aerogel blanket that you see on the top and the bottom left, these vacuum insulated panels, we still have pretty negligible structural performance. That said, there are a few materials that we'll get into here a little bit later that are given a little bit more promise in terms of having pretty good thermal performance and fairly significant structural performance depending on their loading. So being that we don't have that silver bullet, as everybody says, we need to get a little bit craftier, and in terms of finding a balance, it gets to be multifaceted, have to take into account different variables. So looking at structural implications for instance, you know, if we're looking at a 2x4 stud wall, stud space at 12 inches on center, we can get a decent span out of that, 8 feet, for instance, depending on your wind and dead load. But looking at that same constant wind and dead load, we can basically take steel studs and about the same size and increase that spacing and use less material, have less bridging, and get that same span. And then if we want to sit with that same wall cross-sectional area and span a little bit further, we can double up those steel studs, as you could see in that second from the right instance. And then to the far right, we can talk the owner and occupants into having a little bit more area cut in to the overall project and go with a little bit deeper studs. we could get a little bit more span on there, a little bit more efficiently in terms of material use. But that does not come without thermal implications, especially if we're looking at these thermal diagrams, which is just, I call them rainbow diagrams, really just to get a visual idea for where your bridging is occurring. Ideally, you want that layer cake, I guess, the parallel lines that you're seeing to the far left with the wood, which makes sense that you're going to have more of a break there with the steel, with the higher conductance over, about 400 times as conductive as the wood. Stainless steel is significantly less so, as we mentioned earlier, almost 150 times more conductive than wood, but at least we're not looking at aluminum, which is well over 1,500 times more conductive than that wood. But still, so you might say, why don't we go with the wood? Obviously, we can achieve those greater spans. It's also going to be a little bit more durable, like we were mentioning earlier, in terms of condensation and whatnot. So taking that knowledge and applying it to clear field bridging, we've kind of taken our own stab within the office, trying to look at percentage reduction, looking at, for instance, here you see the top grouping, looking at wood studs, see what happens when we have 12 inches on center. If we increase the spacing, you could see that the percent reduction due to an effective R value when you account for bridging goes down a little bit. You can see that when you get some deeper studs, that 2x6 thrown in there versus the 2x4, it's a little bit more material. It's offset by the fact that when you're going with your bad insulation, you can obviously have a deeper stud cavity, which means you have more insulation in there. So that's something you have to account for. And then also you could see what happens when you go to steel. You could see your percentage reduction from the nominal R value once you take into account the bridging to get to that effective R value is well over half in many instances, all of the instances shown here really. And then you start to cover that cavity insulated steel stud wall, and you can see that you start to chip away at that percent reduction significantly, to the tune of maybe even half, but at least another 20%, getting it down to a little bit more reasonable amount. Still not as low as wood, but still, considering the fact that you have a nice balanced, holistic design and performance aspect, that's well worth considering, and it's also why it's well outlined in the code. Now, one thing that you should be considering, I think, we've already covered this here in the previous slide, but one thing, this is where I was trying to get to, thing that you should be considering when you have the bad insulation with your continuous exterior insulation, as you have in the thermal diagram, up to the top right, you could still see that cavity insulation creates a little bit more bridging within that cavity. And so when you see that blue line and the red line, these are based on different humidity levels where the dew point would be drawn in. So if you have your vapor retarder air barrier on that exterior face, which is down, you see, I don't know if you could see my cursor here, but it's on the bottom layer of sheathing is the exterior face. Between that sheathing and the exterior insulation, if you had your vapor retarder there, you would still have some issues with condensation that you'd have to address. So in a lot of instances, what we'll recommend is trying to go with a fully outboard continuous insulation system, which is what you're seeing on your bottom right. The color difference there between that and the diagram above it is showing that there is no bad insulation within the stud cavity. And you can see that your dew point line is well outboard of where your air and vapor retarder would be. And you can see the corresponding reduction factors within the chart to the left. However, once we start patting ourselves on the back for finding that solution, we have to realize again that we have to connect the cladding system back to the secondary structure. And you can see the metal Z's, why they really don't fly, both in the numerical charts off to the left, as well as the graphic to the right. One thing that we've done in the past, say, hey, if you're not going to do that, at least put a FRP pad, as you could see in the rainbow diagram to the bottom left. But if you look at the table to the left, you could see that that only buys you about, up to 10% if you go up to a ½ inch for that thermal pad. So really, to make some decent headway, you really want to go with a FRP Z or some other thermally broken type system. And this shows you some additional strategies. Again, taking that clear field type system at that micro level and looking at it, even though they're not considered linear or point bridges, but you want to take that, kind of reduce those down from using materials as well as layout to do, take them down from a clear field to a linear transmittance, and then even down to a multiple point transmittances by going with those FRP standoffs at a 2-foot spacing, which you can see into the table to the left. You can deal with, less than a 10% reduction in terms of your effective R value. Moving along to examples of linear bridges, the one where we always contend with at that fenestration and opaque transition. One of the reasons why we try to stay away from storefront whenever possible. On the left, you could see a standard where you're bringing your exterior pavement or whatnot right up to the edge, and then as soon as you can, bump out with your below grade insulation. You can see with the rainbow diagram that you really have a decent amount of bridging that's breaking through there. And so say, why not go up to that okay level with the storefront moving down. You can see you get a little bit of headway, but by the nature of the storefront system, you still get a significant amount of bridging until you get towards that kind of better level where we're taking an FRP diving board, if you will, and pushing it out to that where your thermal breaks within that high performance storefront system can really align with the insulation below, and you have a similar condition up at the head. And that's part of the reason why we say if your project can afford it, for durability's sake as well as energy performance sake, it's always better to go with a curtain wall. You can see to the image to the right where the alignment is exactly where you need it, even with a what I'd call a mid-level performance system. Still thermally broken, but not thermally improved. There's no reason why we should be doing that in this day of age, even down to that thermally improved, or but still something to keep in mind in terms of what a standard would be. More to the point, for linear bridging, we're looking at balconies. Here, for instance, taking a PT or conventionally reinforced concrete balcony slab construction, kind of better shown through the isotherm dew point diagram to the left, where you have embedded steel angles both on the primary structure to the left as well as the concrete balcony to the right, and then have a ledger angle that comes out to pick that up. Maybe have a pad, shin pack, separating the two, but for the most part, you still have a decent amount of thermal bleed through there. You can improve that a little bit more by taking one of those FRP pads or FRR, one of these fun plastic polymer pieces that we'll get into a little bit later here in the presentation, and separate that gap. You could see, make a little bit of headway, or using a pre-manufactured component, structural thermal break, which you can see gets you exactly or closer to perfect, I guess, as perfect as you can be. So kind of the best solution that we'd be after here. And then again, that strategy is to, well, instead of taking a continuous bridging element, you want to take it up a notch thermally and limit the number of times that you contact. Take it down to a point transmittance, even from 6 all the way down to 4, as we're showing here. Just easy enough to do with your structural reinforcement layout, and can typically get that to work in terms of your transitions for your other control layers. And, you know, we're just showing a few different items in terms of thermal break materials. One thing that's kind of born out of a lot of our 90.1 committee concerns, those not familiar with thermal break components, there are quite a bit of options out there on the market, whether they're pre-manufactured, very specific, or kind of a kit of parts, very flexible to your own application. So now getting to the nitty-gritty, covering those applications, speaking of which, we covered just before. Excuse me. In the past, people might have thought thermal bridging should just be considered for high-performance buildings like this net zero office building in Phoenix, under construction right now. It's already built, net zero project up in Boulder. So in terms of examples, why don't we start there? For high-performance building, Amherst College New Science Building, last year's AIA Coat Top 10 building, 76% energy reduction compared to the 2030 baseline, which, especially considering that this is a lab building, notoriously high in their energy expenditure, it's even more particularly impressive. Basically, one of the elements that we're going to be looking at here today is the curtain wall. Custom curtain wall spanning up to 65 feet, connecting the labs and the offices. This big bar of light, further maximizing the transparency by offsetting emollients from the glass, skinnied up significantly. As you could see, a pair of 1-inch thick plates for the shorter spans are able to get those plates down to 8 inches deep, offset again, as I mentioned, from the glass with a continuous contact, a steel T on the inside of the triple glazed wall, and that 8 inches with those double plates off the backside grows to about 12, but still quite slender. Structurally, we were able to achieve that by hanging the mullions. Anybody who's seen any of our work before, worked with us, or seen our presentations before, we know that that's a trick we go to quite often. We had to get a little bit craftier with the mullions, a little, slender as they were trying to get, as well as the spans that we were trying to achieve, and fixing the top and the bottom, and even including a nice little canopy cantilevered off the off some of the entrance areas. So you could see here in this cross section, we're speaking of cantilevers, we're cantilevering the roof that comes out to pick up and hang this wall in and of itself, perfing that roof with skylights and whatnot. So a lot of fun. And of course, even though we're having a lot of fun, we need to maintain those lines of continuity in terms of thermal barriers. So 2 points where we had to deal specifically with thermal bridging up at the hanging portion. The first one, so you could see hanging from the roof. Lost my image. I apologize about that. So basically what we had up there to deal with this bridging component, I apologize, at this level, were a pair of manufactured structural thermal breaks, which I'll point out here in a couple other examples. And basically the structural steel members that were making their way through this cantilever portion were broken by those elements. Down a little bit lower, as I mentioned, kind of cantilevering off the hung curtain wall mullion off the backside in order to pick up these entrance canopies with the vestibule. So I have to maintain a tight tolerance in terms of the deflection even out at that free end. And as you could see, the architect wasn't kind enough to give us too much of a backspan. No problem, challenge accepted. It to fit a lot of other things in there. But you could see here in terms of the blue line being our moisture barrier, also follows our air barrier line. And you could see the curtain wall line coming over the top, making its way to the door below, and intersecting that, of course, in the way is our structural thermal break to decrease the bridging at those penetrating beam elements. Now, of course, we wanted to keep the front nice and thin, as many of our clients like to do. So we couldn't go with the same type of thermal break strategy, which is the more straightforward option up as we did up at the top. Instead, we had to resolve a lot of these moments with a combined force resolution of bolts, as you could see here, as well as a thicker flange plate. And how this works structurally, basically where you have your tension in that top bolt, which we're doing stainless steel, so we can minimize the amount of thermal transfer through there as well. And unfortunately, we did not have that high-end $20,000 a seat thermal program that Morse and Hirschfeld did to do the research project in BC Hydro. So we just combined a bunch of 2D elements here to figure out what's happening at those high bridging concentrations, as well as what's happening through that FRP thermal break material. Actually, that was not a FRP break, just another type of break, FRR break. And because we have some significant wind loads coming through here, we have to consider load reversal, that sometimes we're going to get some uplift, other times it's going to be pushing down to the snow and wind, and otherwise we might be able to be a little bit more efficient in terms of our connection layout, even our plate layout. But in this case, we had to account for that symmetry in terms of loading. And going back again to our structures 101, house sections, resist bending. The best way to look at this is, we want to look at a wide flange as kind of our example in terms of our ideal in terms of resisting moment. You want to take that compression load and that tension load and spread those out to the greatest extent possible in order to minimize those resulting force couples at each of those points. And doing so could not only decrease the size of those bolts, it could not only, possibly get rid of those, a couple of bolts as well, minimizing that thermal transfer. We can increase it a little bit more. You can take those full-on square plates and possibly cut them out, making a little bit more efficiency in terms of that thermal as well as that load transfer. Yes, you'd have a few more jogs in and out to reconcile when you come looking at your air and moisture control layers. But still, it's something that could very well be worth considering in terms of arriving to a holistic solution. And there's that pack that I was trying to show, and that thermal break connection up at the roof line where we're hanging. We had a few of those modules connected together. You could see where you have a continuous beam going through, where you have a beam with the end plate, then your contact area is pretty significant, where you're basically looking at those thermal break modules that we're looking at to the top image. What's actually being transmitted in terms of a thermal break is, or bridge through there, the 2 bolt holes, as well as a stainless steel HSS embedded within there. Everything else is high density insulation material. And you could see here, they're quite easy to specify and have some support to help get some pretty high forces, both in shear and moment, out of various module layouts. Now, the next example that we're going to be looking at, obviously, have some other cantilevers and knife edges to contend with. Seeing a theme here. Basically, in terms of structure, how we're able to make those knife edges at those cantilevers happen. Start with the primary structure, basically a truss girder coming out for those primary elements, and then going to a secondary structure there in the blue and cyan, kind of going out to, since they're smaller members, they have less cantilever to make, so they can come out to, you could see, a much thinner profile at the end. And then infill with, I guess if you would say, tertiary or level members. And the thermal line is maintained here. We have an occupiable roof, a green roof up top. See, it comes up and over the parapet like we were talking about before. The blue line, of course, is showing the moisture line. And it's carrying itself all the way down, back down through that vertical opaque portion of the wall and set from the knife edge, if you will, out at the furthermost tip, and down through the sliding glass wall below. And of course, we have to make some structural connections. So we had a couple thermal break locations. In this instance, we're basically taking that point load and creating a bunch of smaller point loads, but since they're spread out a little bit further, we're able to resolve these thermal bridges in shear, if you will. You can see the shear connector. The highlighted areas, of course, being a thermal isolator, which we enhanced even more so with the stainless steel bolts, using thermal isolation washers on each side as well to give yet additional separation. Now, this ends up being, as long as you're not getting that pad thickness, you know, up in a couple inches, I think might be the threshold depending on your load, loads that you're seeing through there. But in terms of your load transfer going either direction, it tends to be a pretty efficient way of transferring that structural load without dealing with severe structural or thermal implications. And there you can see the products. I guess I should have kind of wiped out the manufacturer's plug there, but ended up working quite nicely for this application. As you could see, kind of going back to the interior, exterior, this is Detroit, so we're concerned not only with that energy transfer, obviously when the walls are closed, but also with that moisture sensitive material, that pretty phenomenal wood ceiling that we have going on the interior. So another project, one thing I will say, like all of your sub-consultants probably say, early involvement is key. So as many skin stakeholders as you can have chiming in as possible is better for many, many reasons, including resolving structural thermal breaks. Obviously, your skin consultant as well as your structural and energy modeler. But even when you're looking at, say, a punch window option to a rain screen, self-shaded facade option, to figuring out how those options could actually be constructed, it's always important to be tracking those thermally isolated connections, which we were from the beginning. This is critical not just to begin that familiarization process, but also get some stakeholder buy-in, make sure it's captured in pricing from the get-go so there are no surprises later on. It seems like we're at pricing, which is good, early and earlier, but it's requiring that the design team maybe zooms in to a little bit greater level of detail than we have in the past, and also to coordinate with the whole building energy models to deal with whatever energy goals we might have and carry those through from VMU to the PMU if your project has it, and all the way down into your development and construction drawings. Here again, you're not seeing those cladding attachments because we tried to span more than a couple supports, as you could see. So kind of riding that frequency, breaking those down from a clear field to more of a point thermal conductance. But still, where we do have to connect, you could see there was a proprietary custom, if you will, to this facade manufacturers, almost akin to what you'd see with the thermally broken window system, where you have a couple of dog bones separating that. And then where you have what I call the parapet and plan kind of option, where the fins come out. Again, if you could see the cursor here, you could see to the right that profile against the light outline of the sky, where we're projecting out fairly significantly. We're wrapping those fins in continuous exterior insulation, as well as putting that insulation in these cavities. And that was more for anything else, more mainly to curtail any convection within that cavity. So we're balancing out that condensation potential with respect to that. Something that you kind of have to go back and forth between. And obviously we have the louver areas where you can see aesthetically, we're trying to let that die in, but also in terms of performance, we want to maintain those duct run to exterior insulation continuity nicely and cleanly. And then again, at the true parapet condition, handling very similarly, if not the same as we did with the parapet and plan, if you will, maintaining that thermal continuity from the roof up over and down into that vertical wall, which was easily attained even though we had a few panelized wall contractors, the by others people made out of a few other subcontractors. But still, you could see how we maintain that over the top. Again, there's the wood in the exterior envelope. Again, something I'm not the biggest fan of, even as just a nailer here. This is something we needed a FM global rating, so we dealt with it the best we could. But again, wood's fairly great in terms of thermal conductance. So just in this area, it made sense, and then you could see the thermal break there within that panelized wall system. Now, getting even more interesting, we had a thermal break at the base of the penthouse support screens, as well as some screens at the podium where trying to separate a play area for a daycare system, or center rather. And so one of the things we like to do is not try to resolve that at the moment. So we had a kicker up at the penthouse screen. We weren't so fortunate down at the base. But this, again, as I mentioned earlier, it's a more efficient way of transferring that load and therefore decreasing the loads that we'll see both in primary structure, connecting bolts, which has an effect obviously on thermal performance. But by using any number of these different types of synthetic systems, a lot of these of which can be cut to shape in the field, or if they're frequent enough, it's probably more efficient to cut them in shop, throw them on out, bring them on out, just lay them out similar to how you do your steel. And as you could see, a great number of options with varying R values per inch. A lot of these come into a standard kind of thickness is that 2 inches thick, and then kind of break down from there towards ½ inch, but it depends on that particular type of material, just as those particular materials have various compressive and tensile strengths. And you can see the continuity that's maintained throughout. Another thing to notice, we had the kink in the kicker, if you will, kinked at the end to pass through the roof membrane orthogonally. That way you can use a standard boot at the roofing transition. Yes, locally you'd have a little bit of bending, but at that point it's minimal and you still get that more or less that axial force transfer, maybe a little bit of shear through those bolts. But while your thermal goals and structural necessities lead you to a final list of options, it's important to pay attention to these final refined answers coming from a holistically driven decision. So this is one of those options. And then where the screen support height was too low in certain locations and that didn't make sense to be able to boot that, we went over and wrapped over the top and essentially became mid-intermediate curb, if you will, over which we wrapped and again bat and filled those cavities in order to deal with convection. And then even down at the quote-unquote normal areas, you could see using a pre-manufactured rain screen standoff system. One thing I like to say about these two, talking about holistic solutions, you can keep those penetrations out of those tender lap zones and cantilever beyond those for your cladding attachments. Even you could see a higher concentration of thermal bridges at that soffit area because you're taking a little bit more gravity load. Most often these connections are going to be driven by your tensile load, the pull-out strength into whatever substrate you have, in this case, cold form steel, and also dealing with your loading conditions where it's a little bit higher on that underside with the eddies, that soffit. You can see the final product. I know I'm running a little bit behind. I'm going to keep continuing, if that's all right. Chime in, Mike, if you're going to have to cut me off, but I have no problem moving forward here. I'll try to move forward fairly expeditiously. Here with the art gallery in New York, a similar panelized system. This is replacing an original one-story home of this gallery in the wake of Hurricane Sandy, and also trying to deal with zone green regulations where New York allowed developers and still allows developers to build out beyond the existing FARs if energy performance measures are met. And also in terms of the aesthetic, really, the front side, the architect was dead set on using a Sicilian volcanic stone. Read into that, that's really heavy. And on the side, you could see a foamed aluminum rain screen system, which was actually surprisingly cheap, or cheaper actually, out of Canada, but still, even though it's quote unquote foreign, it was still quite a bit more effective cost-wise. interesting to note too, the textures are very similar, as were the wall systems in terms of the attachment, using these French clips, intermittent thermally broken aluminum extrusions, same ones that we saw from the previous project at MIT, same panel fabricator, installer. And again, looking at the moment, so it's looking at cross-section at that French clip, and then the standoff, you could see the resulting moment to the right side back at the cold form steel stud, as well as the shear between the aluminum and the isolators, a dog bone, if you will, and even at the notches to translate those joints where we had the vertical movement joints between the panels. Wanted to make sure that those didn't interfere or govern the exterior aesthetic, if you will, for the joint layouts. Also, it's important to note too that the aluminum foam we're able to keep 3/4 of an inch to an inch thick, lower dead load, fewer support points due to that lower dead load, and the wind was governing there. Epoxied the aluminum foam voids with a stainless stub or stainless steel stub dowel embedded into that to create a hidden fastener condition. Volcanic stone, it's thicker, denser, heavier, 1.25 inches thick to 2 to 3 inches thick. Certain areas about 10 times as heavy as the aluminum panel. So you could see that we're dealing with a double-edged sword then. So we need more frequent supports, which makes more bridges, which requires more insulation, even though, I don't know, I'm a big fan of trying to deal with the bridges themselves. I've heard someone say the adage where if your thermal bridges are essentially energy leaks, and if you have a leaky bucket, you don't try to fix that by making a thicker bucket. But in the end, it's what we had to deal with the project constraints. You could see more frequent support conditions. And a little bit closer to home, this project pretty much started and began with thermal bridging, both in terms of how the structure was laid out, as well as how the wall assemblies, or actually it's more roof assemblies, except for a handful of panels, maybe 3 or 4 of the many panels that we've had across the project. Started with wanting to do bad infill, wanted to make sure that we had a skinny section as possible, which is why we were trying to deal with the thermal bridging and just kind of suck it up and deal with it that way. Also looking at SIPs, had some concerns about the durability, of course, and especially where you're dealing with some pretty violent, if you will, joins in between the different panels. It didn't make sense to go with a SIP. And so we still tried to go with a basic system where we're going to skinny up those studs to 6-inch deep studs, push all the insulation to the outboard and have a cover board, and then have a rain screen cavity on top of that, still beating the bad insulation option, and increasing the energy performance. And you could see validated, nice layer cake option. And it also was helped by the fact, again, that we were doing the structural engineering for the primary structure as well as the secondary structure, kind of layer caked on one another. There you could see the point standoff structurally from the primary to secondary, trying to maintain those that 6-inch depth. So occasionally we had to have carbon steel going across with the HSSs to break up those cold form spans, and then piling on top of that your tertiary structure and control layers. There you can see the underside, and the rain screen roof being the final element. Again, we have to connect all those cladding members. Here we had intermittent structural thermal breaks. You can see for both the wall areas as well as the roof standoffs. A Z-girt connected into that, spanning between these intermittent breaks. Started from the get-go with these nasty, dirty sketches, and all the way through to some of the manufacturers' marketing materials and their fancy ISO renders. But that started, bridge between those two. Trying to figure out how to lay these out, especially since they were intermittent, was a challenge. And Derek in our office did a fantastic job of laying all of these out. And contractors out in the field did likewise. And then there were some special areas where we really needed to stick with some angles as opposed to those Z's, which really couldn't cut it anymore. So where we did have those instances, we dealt with that 1/2 inch thick FRP pad, which again isn't ideal, but it's where we were able to, it got us there for just a couple of point breaks there. You could see them being constructed, and you could see that's at the entrance when you go in, creating that overhang. And then of course, why stop there where we have the concrete wall as well as the curb going all the way around the building and into below grade insulation. Even with all the geometric fun that we were having, we maintained that thermal continuity. Where we had to penetrate those with a curb, you could see in that rightmost section, where we did have to go through with a rebar, we made sure that those were sealed, of course, and tied into the waterproofing membranes. Also, we made sure that they were stainless steel for not only from the corrosion standpoint, but as mentioned earlier, for the thermal performance. And to maintain that degree of separation between the insulation, well, now we kind of went to the well of the precast concrete manufacturers in terms of doing these standoffs, FRP, carbon fiber standoffs, which were, again, made for precast plants, but have found their way into cast-in-place applications. And here's that money shot, which I usually end this section with, but I wanted you to take a closer look there at the building, and you can notice maybe some interruptions there in those panel joints. That's an area where partway through we found out that the mechanical unit that we were going to be using couldn't be disassembled and taken through the interior. Instead, we had to remove a section of the building. That's also why we have those hexagonal pieces of FRC missing. Instead having a steel grate to allow that for that air intake. And due to the fact that we had some pretty hefty steel members at HSS 16 with 1/2 inch walls projecting through from the interior out into this mechanical well, we had gone through the pre-manufactured structural thermal breaks. You could see the modules laid out due to the geometries. Some of these plates, especially that top plate, were pretty hefty. You could see an inch thick, pretty sizable. But all things considered, once we gave them the forces and confirmed those loads, pretty efficient in terms of the module layout and highly constructible. This is what we were after. You could see the beautiful, even with that pretty significant load transfer from interior to exterior, interior being on the right of that detail, exterior being to the left. We're still able to maintain that layer cake spilling over from the roof down to the wall. We wanted to avoid this, where we're just business as usual, just, well, that's all we can do and deal with it. Could see we had some condensation issues with the thermal diagram. Energy performance, we could account for it, but we're also trying to play that balancing act of, needing a bigger unit to the exterior than needing to cut into the square footage and whatnot. So this was significant enough to stay away from. So we had to actually deal with the fact that that's what we ended up with out in the field, unfortunately. So we were put into almost a retrofit mode. No more manufactured thermal break, which would have been the best option. So we started looking at what was the most effective way to deal with these bridging locations, looking at closed cell spray foam infill, 12 inches to the exterior, 24 inches to the exterior, maybe going 24 to interior and exterior. And you could see through each of these, even going 24 inches to interior and exterior, we didn't want to fill the entire length of these HSSs. That would have been ridiculous, especially considering that these are 16 inches in diameter. Even with that inch of that being taken up with the steel walls, it still didn't give us enough performance to get away from the condensation issues that we were having. So we ended up going with foam glass insulation wrap, looking at 12 inches to the exterior, 24 inches to the exterior, 5 feet to the exterior, and pushing it all the way down essentially to the connection. And you could see we kind of wanted to stay away from this if at all possible, because we were worried about any maintenance that had to occur back here could end up in dents and dings on the insulation. So we didn't want to use your mineral wool insulation, plus it was going to be exposed more or less to the elements. So went with cellular glass insulation, often used in industrial applications such as this, where you need a little bit hardier material. About a R 3.4 per inch, used 3 or 4 of that, or 3 of that for this particular application. And could see it ended up working quite well after that 2 feet to the exterior. And that's what we ended up going with as kind of the plan B, C, whatever you want to call it, in order to deal with the condensation concerns, and since we couldn't have the originally planned intent. And if you'll notice or might have caught through what was mentioned with the ASHRAE slides earlier, it aligned well with what's potentially going to be the required 2-foot minimum lap in these quote-unquote patch areas. So about 5 to 10 years later, it's good to see that. This is a reclad building in Baltimore, Maryland that we did with, or are doing with Snow Krylik Architects. Social Security Administration headquarters, taking a pretty well done with facade. It's kind of upgraded. You could see based on the gradient on that front facade, this is the north facade, where it's reacting to the solar exposure throughout the year, more opaque around those edges, especially on the south and east and west facades, but as it wraps around on the north elevation as well, you can see it dies into more of a fenestrated facade. And this is one where really the facade was doing the heavy lifting. We couldn't really grow the capacity of the central plant for several reasons. And so that was really driving not only the performance of the project, but even the concept design length, taking up a good chunk of the overall schedule. Working with HGA mechanical engineers in Minneapolis, went through various options, exploring envelope areas and percentages, window-wall ratios, trying to figure out sensitivities based on elevation, where we could have more glass, where we needed to hyper-insulate and whatnot. And even within those areas, figuring out which performance aspects really got us the bang for the buck. A great number of analyses ran, not only on their side, on our side, we gave them micro models to feed into those. And also we had a requirement for LEED certifiable, which was driving a lot of it as well. And when you're at the base, you have the entrance to, again, the headquarters. So this canopy projecting through at a slab edge, through the curtain wall, one of the nice knife edge again, glass overhead. And you could see where it's tying into the slab edge of spandrel beam, which again, structurally, that's great that we had it there. In terms of thermal performance, again, a concern. But being that we had an existing building, we, as you can see with the image to the left there, concrete tolerances weren't exactly how we were hoping. So we had to go back and do a retrofit analysis. You could see changing from carbon connectors through bolts in that second to the right detail, that blue, and going for a lighter blue with that stainless steel. You could see how it brings that dew point in further. The dew point was driving this particular condensation analysis, was driving really the guts of this detail, most finite level elements. And you could see it here in plan as well with that structural thermal break. In this case, again, the same type of synthetic polymer material, flange plated between the steel T, inverted steel T to the exterior, you could see, and the concrete spandrel. You could see to the left where the curtain wall is going to be also carrying a load through there. So the load path here is multifaceted and a little bit further away from being straightforward, but I think well worth it in terms of the overall design. As you could see, this was taken a few weeks ago. And for direct line of sight element like a canopy that at the ground level, crisp detailing, of course, is expected to be crucial. However, if you're familiar with Snow Krylik's work, you'll know that they pay the same attention to the parts high above. Here's some studies looking at the joint line up on the tower, trying to figure out what happens if we bring the horizontal through versus the vertical through, etc. And they took that all the way up to the tip top, wanting that crisp edge at the front of the leading edge of the parapet. You could see that from the previous projects, we love carrying that insulation over the roof, over the top, and down to the vertical wall assembly. But this wanted to be a little bit skinnier. So in order to make that happen, we have the adhered insulation off the backside of the parapet, wrapping around over the top with a cover board because you have the high temperatures underneath that coping. And then where we had 6 inches inset from the exterior face, we had to put some of that high performance blanket insulation, as well as use an FRP diving board, basically capping from, I don't know if you could see my cursor again, going from the back side of this parapet and resting on the top of this curtain wall, and also being the clamp for the coping off that front edge. So there's a thermal line. You'll see the picture of the FRP being installed. Again, contractors were scared of this, and we're seeing more and more after they deal with it once. They just factor in their bids. They have to buy a few more saw blades, but buy sheets, just like they buy sheets of plywood going over the top, keeping this continuous throughout. So thermal bridging in the real world, obviously those were trying to push the envelope, if you will. Pun unintended, but sorry anyways. Now, we've been incorporating these structural thermal breaks pretty much as an office standard for just under 10 years, and we're sometimes told, like with the science pyramid and our expansive, crazy glass projects such as this, you know, well, yeah, if we had special projects, conditions like that, we'd be doing thermal breaks all the time too. And in fact, this would be so much easier if we did not deal with thermal bridging. So I think one thing to take away from this, if you would please, is that we don't do thermal breaks because of the crazy geometries. We do them in spite of them, whether it's started out with monolithic glass for our glazing projects, pushing that to insulated glazing units, and the same thing here with bridging. That said, our more straightforward projects, starting with, you know, what you see all the time, anchor brick veneer walls. To deal with this, I don't know, maybe some of you have seen these manufactured assemblies. There's several out there which push that that thermal transmittance off the wall by connecting that ledge angle out a little bit further so it's not continuously in contact with the floor edge. This is what we'd see in the past. They're post installed, or it could be with an embed or whatnot. That's a little bit cheaper way of going about it. However, if you do kind of a kit of parts, this is part of the economic study that we did for the ASHRAE program. Actually, we figure out that because you don't have to cantilever as far out from that face of wall, you can end up with a more efficient angle profile for that ledge angle, and basically just build this out of a kit of parts out on site if you wanted to. So it actually ends up being the cheaper solution, maintaining that continuous thermal line. There's a CLT project that we have in Minneapolis. By the time it gets built, it's said to be, or slated to be, the tallest CLT in the country. As many as are going on out there, it's probably going to be eclipsed fairly quickly. But even though wood has a lot of thermal benefits, with CLT, there's a high concern in terms of condensation and durability. So with this particular CLT structure, it's a composite system. So we ended up picking up those exterior balconies, tying those into the concrete structural topping that then works compositely with the CLT floor system. And we didn't even mess around with doing a thermal analysis of what that would have been if we just carried that thermal bridge all the way through. Actually, for our own knowledge, it's something we'll probably go back and do, and so stay tuned for subsequent presentations. But this is how we're ending up handling these systems. One way we could have gone, again, like we covered before, is reducing those linear bridges to point bridges and reducing those even further. And now, if you're on an even tighter budget, especially here locally, working with Path 21, Red Rocks Credit Union, you could see some pretty significant overhangs. You could see our structural drawings where we had the structural thermal break back at the wall line, listing shear and moment loads, working with the manufacturer to figure out how many packs we needed, and you could see that fairly efficient. So 4 per each of these. These end up being about a couple hundred or so per module. So it behooves you to be a little bit more efficient in terms of laying these out, and it's easy enough to do with the experts and manufacturers themselves. And even in a maintenance garage with RNL at the time, now Stantec, again, we had some overhangs. We had some significant bridges. Even just for a garage, you could see well daylit. They cared about their employees. Even on the precast wall panels, all the way down below grade. maintaining that thermal continuity with the aforementioned isolators. Now, one thing, if you have a building like what we're working on now, increased surface area, it's going to increase the amount of bridging, especially when you have some balconies protruding. Ideally, you want to do these manufactured structural thermal breaks that I was mentioning on the timber project. These are very, very expensive. They're not like the previous modules that we were showing. So they can be cost prohibitive. Couple options of getting around this are the option to the right, where you're taking that below slab insulation, pushing it out for a slight overlap, and having slots within the structural system. This requires kind of some tight coordination, early coordination with your structural engineer. Otherwise, you end up with the below slab insulation only over to the left. Obviously, not as ideal, but again, that overlap, pushing that thermal transmittance further towards the outside so it doesn't have as great of an effect as it would otherwise. So one thing that we've looked at in terms of your structural system, if you're going with a column strip, flat slab, one-way slab system where your column strip is really, in essence, a big flat beam. And then in between those column strips, your slab is spanning from column strip to column strip. At that wall line, it doesn't matter as much if you cut a slot in the concrete slab, and actually better than cutting, casting that void in there. So, and infilling that thin with insulation. So kind of your poor man's thermal break. So there's what you're seeing in essence. If you want to take it a step further and be cost effective, but also be somewhat frugal and cast in those slots, but still take it up a notch, even at those concrete column strips, using a pre-manufactured thermal break, but only do it where you absolutely need them. So finally, at the end here, I apologize for going over so long. Just wanted to throw the rest of our team up here. I know it's me presenting, but there's a lot of work put into this. Always a team effort, and not just our company itself, but obviously the clients who kind of are the other stakeholders who really believe in this as well. I mean, and make it happen, not just through design, but realization as well. So with that, I'll say thank you very much. And I don't know, open it up to questions if anyone's still on.
All right, thanks, Will. Why don't you unmute your video so we can see the man behind the curtain, pun intended. I wish it said curtain wall.
All right.
Well, we do have a couple of questions from our attendees that we'll get to, and thanks for a great presentation. That was terrific. It's good to
Thank you.
Good to nerd out a little bit in the middle of all this.
Yeah.
And I don't know of a calculator that would run that formula you showed earlier in one of those slides. So we're glad you're here to do that instead. So first question is, does the International Building Code typically consider FRP or some of these other synthetic connectors combustible? And does that present issues with some of the fire rated wall or roof assembly requirements?
Yeah, I guess kind of going with the IBC themselves, they're, that's pretty straightforward. Looking at the NFPA 285, I mean, it's straightforward in terms of, yeah, they want every assembly to be tested, every component combination to be tested. And it seems like more and more code officials, authorities having jurisdiction, they're a little bit more reasonable in terms of how constrained that requirement can be. But there's, quite a bit of testing behind a lot of these manufacturers' FRP components, and they offer that up So I guess in terms of the IBC and NFPA 285, they just make you account for it. But it's really looking at that building official in terms of what they're going to reasonably require.
So you can probably rely on those manufacturers for some advisories or bulletins or test results if that question comes up.
Exactly.
Okay. And then some of the projects you showed had some fins or some large projections from the facade, forming shades or even decorative devices. Were there any noise or vibration studies that were carried out as part of that for structural adequacy or serviceability or even interior comfort, occupant comfort?
I'm trying to think with the MIT project. I know the PMU had we had a full battery of your standard dynamic rain tests, water penetration tests, and part of that was taking it at a skewed angle as well as aligned with that long face and I think that was something that they were paying attention to. I don't believe we had strain gauges or anything like that to fully document that. We have had, say, some projects that are more of a decorative scrim, if you will, coming off of that, the Hudson Yards project. We have one here, Colorado State Water, with HCM in town as well, where, you know, it's definitely going to be a consideration, especially when they're perforated. Not only just vibration, but also in terms of noise, that could be quite annoying in terms of occupant comfort. And not just that, but I mentioned, you know, flashing here and there, and I kind of didn't really, well, it took too much time as it was, but I kind of mentioned here and there that your transitions from those air and moisture membranes as they wrap up and over these should be, you know, a prime consideration, because if there's a lot of movement at those particular locations, that's going to accelerate the aging of those particular transitions.
Yeah. I know thermal bridging is just a concept that people are paying attention to. Has come a long way in a short amount of time. Maybe more people were aware of it in other parts of the world than we were here, but I watched in Chicago as the Aqua Tower went up, and it's a beautiful form, but it sort of reminded me of an old motorcycle with the radiator fins that, you know, allow that heat to transfer. And sure enough, the same thing was happening there. So lesson learned, and more people are incorporating some of that. How much of the those thermal barriers, it's kind of a chicken and egg question, right? So the manufactured barriers, are they being driven as a result of the design decisions that architects and engineers are trying to make from a form point of view, or are they providing these, which then allows the designer to make more bold moves?
I'd say it's more the former, especially being a part of the standard process, trying to get this. It's definitely staggering, you know, kind of a lockstep kind of a process in some instances, because it's true. I mean, a lot of these high performance buildings, you know, those options are out there, and whether or not you want to just do it to the hilt and throw it everywhere, yeah, you're going to need to account for those with those types of products. In terms of market transformation, we need to be a little bit more cognizant of not blowing up, not just, you know, contractors, manufacturers. Again, the manufacturers are out there, but contractor familiarity, owners, you know, getting those financed, as well as the building officials being familiar with those, knowing what they're looking at when they do their plans reviews. So I'd say it's maybe a little bit more of the former, but yeah, again, they're definitely in tandem.
Great. Well, those are the questions we had. I do want to remind people, if you want to ensure that credit is received for today's presentation on your HSW forms, please put your name in the chat feature, and that will help us get that recorded properly. And also want to let you know that tomorrow we've got a presentation with how the state of Colorado is adapting to COVID-19. We're going to hear from some state officials who will bring us up to speed. And then as usual, we have events, more of the same coming down the road in the weeks to come on Tuesdays and Wednesdays. So we look forward to seeing you in those future presentations. And I just want to say thanks to Studio NYL and to Will. It's great to have one of our own on a national leadership level, sharing the best practices and shaping the standards based on the experiences that design firms here in Colorado have had around the country and around the world. So, Will, thank you very much for this great presentation and for all you do to help advance the profession.
Great. Thank you. Thanks for having me.
Great. We'll see everybody next time. Take care.